Okay, so up next we have David Hogg, who's going to tell us about physics-motivated design.
Thanks. This title was assigned to me by somebody. It's Siddar's fault. And since this meeting was supposed to be, well, is it partly about generating some ideas for like science development? This talk is not super specific and technical. It's a bit high level. So, and it's designed to inspire conversation, shall we say. So I might say some things you disagree with, that's the point, and we can discuss. And I think I have too many slides, so I might go over some parts of it a little fast, but you'll see what the subjects are, and we can come back to them in question. So what I'm going to tell you, what I'm going to say is that AI and machine learning do not share our values, meaning they don't have the same values as scientists, scientific values. And that's come up in the talks actually this morning. Real data taking systems break symmetries. So even though the physics has very high symmetries, data sets generally have very highly broken symmetries. I'm going to suggest a way to restore those symmetries, which is by putting causal structures. This talk is going to mainly actually be about causal structure. So how would you structure a data analysis so that the symmetries are restored? I believe that the big impacts of AI and physics will be in nuisances, meaning things like auxiliary theories, calibration, and things like that. I don't think, in answer to my question I asked Anna, I don't think that machine learning will answer our true questions, like what is the dark matter? And then I have some things about passive symmetries, which I might not say very much about. Okay, good. Are we talking about artificial intelligence or machine learning? I'm only going to talk about machine learning because that's all I know about. I think also about some artificial intelligence things, but they tend to be in the area of like operations, like integer programming type things. We do some stuff like that. And I think for most of us, AI is machine learning. I have then a definition of machine learning here. It's incredibly inclusive. Not everyone would agree with it. But in my view, a method is machine learning if it becomes more capable as it sees more data. And I mean kind of very much more capable. So not just like square root of n, not just you measure Google better, like truly more capable. And so that includes PCA and k-nearest neighbors and linear regression, as well as all the fancy things people in the room are doing. So I want to have that broad definition because I want to count some things as machine learning. And the key thing here is that the next point is kind of philosophical point, and some of you have heard me rant about this before. Machine learning has a kind of ontological, these points are ontological and epistemological. The first one below, only the data exists. The ontological point is that there's only data. For machine learning, the latent structure of your model doesn't matter very much as long as it makes good predictions. Like when we were talking about discovering new materials this morning, nobody cared what the internal structure of that thing was as long as it predicted new crystal structures. So that's an ontological point. The existence of the data matters. The existence of the latent space don't care. And actually, things like stochastic optimization, like stochastic gradient, dropouts, all the early stopping, all the ridiculous things people do in machine learning shows you that nobody cares about the latent space at all. If you cared about it, you'd optimize correctly. The only arbiter, so the other point is an epistemological point, which is that the only arbiter of truth for machine learning systems is performance on held out training data. That's it. If you perform well on held out training data, it's a good model. And that really is in opposition to how we feel as scientists. No one thinks that general relativity is a good model because it works well on held out training data. In fact, it doesn't even have training data. Good. So what is the point of physics? I don't know. That's a little hard to answer. This is a little grandiose, but I don't think it is to generate data. And maybe it could be to generate data. Maybe it could. But my point of view is that the main products of physics have not been data generations. They've been understandings of latent structure and so on. And I think that physics is really about the latent structure of the world. We are trying to find out what is the latent structure of the world. And there's tons of latent objects like on the last line there, I say like dark matter is latent, right? That's what the word dark means there. Gluons, like they only exist in bound states. Black hole formation, like what is the history of the black holes? That's a latent thing. You're never going to observe the formation of the black holes, and so on. Okay, good. Good. So where has machine learning made enormous discoveries in physics? Good, we're done with that. But machine learning has, however, been extremely useful in physics. And so here's some that come into that are in my domain. One is in the cosmic microwave background is the primordial light from the Big Bang. When you observe it, it's confused by all sorts of foregrounds coming from our galaxy and other galaxies along the line of sight. Machine learning has been critical to that foreground removal, to separate the components and remove it. And that's kind of a causal thing. We're going to come back to causal. In the Sloan Digital Sky Survey, which was sort of where I got my start thinking about these kinds of things, the quasar and galaxy spectral models we used in order to determine the redshifts were completely data-driven with the kind of modification of PCA. And those models allowed us to make all the redshift measurements, which allowed us to make the big maps from which we discovered the baryon acoustic feature. We could never have discovered the baryon acoustic feature without that. If you don't know what the baryon acoustic feature is, I pity you because it's the most beautiful thing in all of cosmology. I would come back and talk about it, yeah, I'm supposed to talk about machine learning. And then another thing we work on is very, very precise measurements of stars, in part to discover planets and other kinds of anomalies. Good. And in there, one of the big issues is instrument calibration, because you're trying to measure the velocity of a star. Actually, the current goals for stellar radial velocity measurements is 10 centimeters per second. We need to measure, if you want to find Earth-like planets, you need to measure the radial velocities of distant stars to 10 centimeters per second, which is pretty slow. And that means you really need to understand your instrument extremely well. And we started using machine learning to understand instruments. Good. Now, generative models. The last thing I need is more data. It would only confuse me if you gave me more data. So I actually don't need a generative model directly. And so we had a long conversation at lunch about what does it mean for generative models in physics. And I think for us, it's more like we're repurposing the subparts of these generative models, but I'm not sure. There's an interesting question asked. But I wanted to make actually just a purely terminological point. In statistics, a generative model is a likelihood function, right? Because a likelihood function is a probability for your data given your parameters. That means in principle, you could sample from it. So in principle, you could generate. And there's an old school, I've used generative model in my papers for 25 years. But it has nothing to do with the things that we've been talking about today. Anyway, it's just important to remember that there's this concept of a likelihood function. Because, and this is a side point, but I just wanted to remind you, it relates to the complaints I had after the materials talk, is that I really care about precision measurements. We make precise measurements. If you care about precision measurements, then you have to be very careful when you're talking about a posterior, and when you're talking about a likelihood, when you're talking about a prediction, and when you're talking about a measurement. And in general, machine learning systems make predictions. They don't make measurements. And you have to be very careful that you're using machine learning in your system at the place that you need a prediction, not the place that you need a measurement. So for instance, you wouldn't want to ask the machine learning to give us the radial velocities of the stars, because then they would be posterior estimates of the radial velocities of the stars, and they would be biased, and then we would not find the right planets. But it's okay to use them to get posterior information about the instrument state, because that's not what we're trying to measure. Anyway, this is a very subtle statistics point. I could talk about this for hours, but it is very important. There's a kind of difference between a likelihood and a posterior, and machine learning systems kind of produce posteriors in a certain weird sense. Actually, some people this morning were talking in that language almost exactly, which was interesting. Blah blah blah. I'm not gonna belabor that, but I have a whole toy model that shows that if anybody wants to do that. Good. So I want to talk about symmetries for a bit. A lot of what's interesting about physics and machine learning is symmetries. People have mentioned physics informed. and my title that I was given was physics motivated. So obviously symmetries come to rise, and I would just want to say that there's two kinds of symmetries, and they're often conflated for good reasons. They're very conflatable. They're highly conflatable. And passive symmetries come from investigator choices. So for instance, there's a symmetry that you can change the unit system in which you work, and all of the physical predictions stay the same, called sometimes dimensional analysis. That's because it's a choice. Your unit system is a choice. So obviously the physics has to be independent of it. God did not tell you what unit system to use. Although some physicists believe that CGS is the unit system of God. They're wrong. Similarly, you choose a coordinate system. In this room, you can choose X, Y, Z in any directions you like. It doesn't change your predictions about anything. Those are passive symmetries. Then there's active symmetries. Active symmetries are like observed things. Like it actually is the case that the law of gravitation is isotropic. Like if you have a mass here, the force towards that object always points towards the object and depends only on the radial distance. That is an active symmetry in the sense that you measure that symmetry to be true, and you can work off of those measurements. It's a bit of a subtle distinction, and in fact, I can easily confuse you about this. And Herman Weil's book. By the way, Herman Weil wrote this very good book on symmetries with a very mathematical point of view. And I don't have the full reference here. It's the famous book on group theory. But anyway, it's beautifully written. And in the opening, he talks about the difference. When you're making a transformation, are you taking all the vectors and rotating them, or are you taking your coordinate system and rotating it the other way? And for Weil, those two things are identical. But for physicists, I don't think they're identical. Because in one, you've intervened in the system, and the other, you've just made a different choice. But I can get you really confused because I gave this example of Newtonian gravity. It's both the case that it's observed that it's rotation symmetric, and it's also the case that it kind of has to be unless there's some other latent field in the universe setting some local orientation. So it's very confusing. But I just wanted to bring it up because it means that symmetries, the reason I bring up this passive active symmetry thing is it means that there might be symmetries acting even when you don't think there are. Like in this room, there's a big difference between down and sideways, because you tend to stand on this surface, but you don't tend to stand on that surface. So the room is not symmetric, but it's very useful to describe the laws of physics in this room in a way that is coordinate free. Oh, gauge symmetry. Physicists love gauge symmetry. Gauge symmetry is a super interesting one because it's obvious that if you don't know what gauge is, good. It's pretty confusing. But it's obviously a passive symmetry. You make a gauge choice whenever you describe a physical system, but it's also obviously experimentally verified in the sense that all successful high energy theories are gauge theories. Strange. Okay, good. So now I just want to go to, that was all the introduction to CNNs, because I wanted to talk a little bit about CNNs. One of the reasons I think CNNs are so interesting is that a CNN, if you think of the CNN, the convolutional layers in a CNN, they exactly obey a certain set of translation symmetries, except for the edges of the images. But you can work on the torus if you wanted to. But anyway, at the edges of the images, okay, whatever. But for a large part of the image, they exactly obey integer pixel shifts, so translational symmetries. But almost no data set that anybody cares about has translational symmetry. Like if you go to ImageNet, or if you go to pictures of profile pictures on Facebook, or if you go to MNIST, you don't have translation symmetry on those images. And yet, using CNNs was way more effective than using fully connected systems. So that makes me think that there's a symmetry. So I have a conjecture. My conjecture is that CNNs impose a causal structure on the images, that at small scales, the image is composed of translationally invariant things, but on large scales, there's a compositional model which is not translationally invariant. I believe I know how to test this conjecture, but I haven't done it yet. But I believe this is and this is sort of one of the hints that says to me that causal structure might be a good idea. So if you think about all the, like if I wanted to find all the faces in this room, the faces are all over if I take a picture, the faces are all over the place. So I really need to do translationally invariant things to find all the faces. However, if I want to recognize that this is an audience in a seminar, that has non-translationally invariant things about like where the tables are situated and how people are spaced out. Anyway, that's just a thought. We'll come back to causal structure. We'll say a lot more about it. By the way, there was a very interesting thing in Anna's talk where she said sometimes it helps to go to the Fourier domain. And Phil Freeman's in the room over there. He's a big believer of the Fourier domain. And it's always surprised me that we apply the nonlinearities or the actuation function in CNNs in the Fourier domain. I mean, in the pixel domain. There's a whole set of domains that are translationally equivariant you can use. Pixel domain is one of them, Fourier domain is one of them, and there's a huge set of wavelet transforms in between, and it would you wouldn't break translational symmetry. Anyway, there's a lot to do, I think, even in CNNs. Here's another conjecture for people, if anybody wants a side project. I believe that CNNs are diffeomorphism covariant, meaning I believe you can distort the seed and the CNN will basically do the same thing, the thing it did before, whatever you're doing, like recognizing panda bears. You can distort the seed and it will still recognize the panda bear just fine, as long as the distortion isn't too severe. And that, if that's true, that means there's a group structure to every layer in the CNN, not a full group, but like a local group structure that has to do with small diffeomorphisms. And if that's true, we could make better things than CNNs. Okay. Just saying. Open science, baby. Anybody wants it, it's theirs. Okay, good. Now, one of the things that people are very excited about in machine learning, physics-inspired machine learning, is the symmetries of physics differential equations, like unitarity, Hamiltonian dynamics, Lagrangian dynamics. And these are very strong symmetries, extremely strong. They lead to all the conservation laws. Right? These are the things that protect all the conservation laws. And they are very useful in emulation tasks, but to my knowledge, they have not been important yet in data analysis tasks. And my job that I was assigned by Sid was to talk about data analysis. I am going to get serious and talk about data analysis, I promise you. Good. Okay, so one question which came up in the morning and was answered to my liking is imposing symmetries good or bad? And the pro on that is physics is extremely symmetric. It's filled with symmetries. In fact, one of the things that's going on in theoretical physics these days is people are finding new symmetries that people didn't even know were there. There's symmetries hiding in GR that weren't known. The cons are that possibly imposing symmetries will somehow make your model too rigid and will fork optimization. We learned that DeepMind does not think that this morning. After all, machine learning philosophy is like build out the latent space and let the data solve your problems. And another idea is that with the thing I mentioned earlier is that real data sets are not symmetric. Even though the laws of physics are symmetric, the real data are not symmetric. So I'm now going to answer these two objections in turn. So I'm going to start, and I'm not going to have very good answers for either of them, I have to say. I'm not confident that employing the symmetries is a good idea, but I'm going to tell you why I think it won't work optimization, and I'm going to tell you why I think you can still use symmetries in real data. Okay, good. Here's the most hilarious reason. This is one of the best math results I know in machine learning. In machine learning, there aren't that many mathematically proven things. Here's a mathematically proven thing. It's unfortunately has a ton of conditions. It's hard to prove this. Okay, so it's a ton of conditions. One is if you have a metric in function space, meaning you can tell me which two functions are near and which two functions are far, So you have a sense of nearness in function space, one, and you believe that the function you're looking for is equivariant to some group G. Two, three, your test data are drawn from a distribution that is symmetric with respect to G, invariant with respect to G. Okay, brutal set of conventions, of assumptions, but then you can show that the closest equivariant function to whatever you train to will do better than whatever you train to. Meaning you could train an arbitrary model on your data, and then when you're done training and you're like, I'm good, then a kid could take your model, move it to the nearest equivariant model, and it will do better. Proofs, baby. Those two archive papers have proofs. I think that's very strong. There aren't many proofs. That's it. So by the way, notice that that says that being equivariant is good, and it doesn't fork optimization because you can do it afterwards. The problem is it's hard to have a metric in function space. Hush. Okay, good. My current approach that I've been focusing on is using invariance. And I've been doing this with Soledad Villar, who's been mentioned a few times today, who's at Johns Hopkins. The idea is that you can always make an equivariant. By the way, I use the word covariant here because that's what physicists call things that obey passive symmetries. They call them covariants, like general covariance is the symmetry of general relativity. But anyway, I mean that you can create both equivariant and invariant functions out of the invariance. And there's a set of papers by Soledad Villar and me that work through different cases of this. Like we show that rotation and translation, rotation equivariant functions, translation invariant functions, permutation equivariant functions, units covariant functions, and so on can be built out of invariance. And then you can run your machine learning on the invariance, and then build out of the machine learning results on your invariance, you can build your equivariant functions. And the reason I think this answers the optimization problem is you actually don't have to change your machine learning structure. You just put different things into the bottom layer. You turn your data into invariance, and then you run on the invariance, and then you unpack into equivariant functions. Anyway, we say a lot about that. The key paper is called Scalars Are Universal. I can put the archive number here because I'm an idiot, but anyway, it's easy to find. And the fundamental result is that in that paper there's many results in this paper, but the sort of fundamental one is that you can make an equivariant vector valued function out of the inner products of the vectors, and then multiplying them back into the input vectors. Anyway, blah, blah, blah. Oh, by the way, I mentioned here Einstein summation notation. I don't know how many people here have taken GR, but if you take general relativity, you learn this notation, Einstein summation notation. And when you learn it, you think you're just learning a trick so that you don't have to type so many symbols, but that is not what you're learning. You're learning a way to ensure that whatever you write down is generally covariant. And so it's a very, very beautiful thing. And you can actually derive a lot of physics things just from the form of Einstein summation notation. That, by the way, is misnamed like most things. It was created by Ricci and Levi-Civita. And it's actually called, I think it's called the Ricci calculus in math. They taught it to Einstein. Levi-Civita taught it to Einstein is what we believe. And then it got named after Einstein in physics because, you know, we are terrible. And I just want to, I'm throwing this up here. I'm throwing this up here to show, this is one of the demonstrations that the scalars are universal thing works. And I'm just throwing it up here to remind people that most of the physics informed machine learning stuff has been done on completely trivial toy systems that nobody cares about at all. And that's for a reason, because it's actually hard to find data sets that are actually exactly symmetric and you have all the latency you need, you know, or have all the observables you need. So it tends to be done in toy problems, and I'm embarrassed by that, but very fun. And right now we're building out from that. This is Wilson Gregory's investment in Johns Hopkins. We're building out from that a replacement for CNNs. So we're trying to build a replacement for CNNs that obey an additional set of symmetries. We're working on that. Anyway, good. Long story. Okay, one thing, here's the fighting words. Physicists love to say that when you have a symmetry of a conservation law. Not true. It's only if your system is Lagrangian that a symmetry implies a conservation law. And that means if you put a symmetry into your neural network, you will not get a conservation law out of it, because your neural network won't be a Lagrangian system in general. There are Lagrangian neural networks, but if you're just using symmetry, you aren't actually capturing the conservation laws. And right now, people don't really know how to put conservation laws into machine learning. There are some attempts, but it's actually quite hard to put conservation laws in unless you're working Lagrangian. We have a proposal. Soledad Villar and I are working on a proposal which has to do with adversarial training. But I think one of the things that's interesting about conservation laws is, like, conservational momentum is a pointwise symmetry. It's not that if you add up the whole system, the momentum stays the same. Well, it is that, but it's also that if you go to any subvolume of your simulation, the momentum in minus the momentum out has to be the change in the momentum in that volume element. So it's a very strong, it applies every pointwise to every location in your simulation. So their conservation laws are really strong. So probably we should be using them. Okay, good. Finally, we're getting to the point. I keep saying this, real data sets aren't symmetric. The universe is isotropic and homogeneous, as you may know. That is very well tested. Actually, I've spent some of my life writing papers showing that it is isotropic and homogeneous. I'm writing one right now. But you're always observing the universe from some telescope in somewhere on a single planet that's inside a dusty galaxy. So the data set you get of the universe is not isotropic and homogeneous. The world is units covariant, but usually your data set always taken the same units. Gravity is rotation covariant, but we're in a lab with gravity pointing that way, all those things. So real data are not symmetric. And here's an example. Here's two quasar samples. Currently, that Quia sample we just made, that's Kate Story-Fisher, made that with the Gaia data. And we're actually using that sample to show that the universe is homogeneous and isotropic. We're using it as that. But if you look at that data set, it's not homogeneous and isotropic. There's a freaking break in the middle of it. And if you go over to the SDSS quasars, it's even worse because the footprint of the survey was worse. And I would call those things selection functions. There's been a selection function applied that means that this isotropic homogeneous distribution doesn't look that way in the data set. And I just learned at the coffee break that particle physicists use a different word for that. It's annoying. Every single subfield of science uses a different word for what astronomers call the selection function. The acceptance. Oh my God. Actually, one of the things that we should be doing, we are interdisciplinary scientists in this room, we should be writing translation dictionaries. I know a ton of translations for different machine learning things that are called different things in different fields. Like everyone loves the fact that Gaussian processes are called kriging if you're in geophysics. And anyway, we should be writing those translation dictionaries. Oh my God. Okay, good. So I believe that causal structure solves all of our problems. So now I'm just going to say a few words about causal structure and then I will give up. I believe that any real data set, at least in astrophysics, but I think this is probably true in every area of physics, has three causes or three things that are affecting the data you get. One thing is the fundamental physics you care about. That has to be affecting your data, otherwise you're making a big mistake. So I'll give you a specific example in a second. Second thing, there's usually auxiliary or nuisance parameters as well. So if you're measuring like the variation of the gravitational field locally, you have to worry about the fact that it's rained recently and there's like changes in the water table outside your building. Those are like auxiliary things. They're physical effects that are directly affecting your thing, but they aren't actually the physics you're looking for. There's kind of auxiliary physics things. And then there's just straight up instrument calibration. Sometimes they're just features in your data that are created by the instrument, and instruments have to be calibrated. Every pixel of every detector has a different sensitivity to light at different wavelengths, and you have to know all of that if you want to if you want to deliver correct data. You have to understand it. And we tend to think of it as correcting the data, but you could think of this as all part of the forward model to your data. If we were making a generative model, the generative model would have these three components and then create data. And just to be very concrete, when we do physical cosmology, like with those quasars that I was showing you. There's a fundamental model, which is the cold dark matter model, which got the Nobel Prize in 2019. There's the auxiliary model, which is how do quasars trace the dark matter field? Where are the quasars with respect to the dark matter in a cosmological model? And then there's the instrument model, which includes which quasars did we select and what quasars did we miss. And we have to know all of that in order to make a precise measurement of the fundamental model. And some people care about quasars and they consider the fundamental model to be a nuisance as well. I'm gonna take the approach, I'm gonna assume that cold dark matter is what I care about, and the auxiliary model is where the quasars form, because that's what I do. And I believe, I don't know, but I think probably almost all physics measurements have this structure. But I don't. Like if you're measuring the Higgs, you have these Higgs events, but then you also have these confusing events that are also in there. So there's like foreground models in the instrument, and then there's the instrumental sensitivity. So I think it works for like Atlas and CMS. Is this a CMS institution or Atlas? We're Atlas in NYU. Good. So instrument calibration. So now I'm going to now suggest that there might be a way to actually. So look, if I could actually model a data set this way, you see how now I could actually get the symmetries, because models 1 and 2 are going to obey symmetries. Model 1 has very high symmetries. It's our fundamental model of cosmology, immense symmetries. Model 2 has symmetries too, though, because it's just about the physics of quasars. That has to be like unitary evolution from initial conditions. It has to be rotationally invariant or equivariant and so on. And 3 could be crazy, but you can see how now I have symmetries to play with. I can put symmetries into these components if I think of the thing as being generated by these 3 components. So instrument calibration, this is a problem I work on a lot. I'm the only astronomer in the entire world who believes that instrument calibration is fun. Everyone else considers it as a nuisance, and I love it so much. I've even thrown meetings about instrument calibration, which people are begrudgingly sent to. Anyway, the best way to do instrument calibration is to have very heterogeneous data. You want every star you're observing to be observed in every instrumental mode you have accessible to you. And you want every instrument, you want every star to have seen every instrument, and you want every instrument to have seen every star. You see, if every instrument has seen every star and every star has seen every instrument, then your data are going to be like an outer product of an instrument model and a star model. And you can distinguish those two things. It's like a low rank. Your problem will become low rank. And there's no reason that you have to think of it as linear. That your star model can be some horrendous nonlinear thing, and your instrument model can be some horrendous nonlinear thing. But you'll be able to distinguish them because the whole system will be low rank in some very relevant sense. That is the basis for causal inference. That's what acts as causal inference. And there's a couple of papers written there where we actually implement some calibration systems. And actually that attitude towards calibration was first used in optical astronomy by us in the Sloan Digital Sky Survey, and became the way the Sloan Digital Sky Survey is calibrated. We weren't first, though. The first people to use this were the CMB people, because the cosmic microwave background is very hard to observe because it's only 2.7 Kelvin radiation, so very hard to observe. So the first use of this kind of instrument calibration was done in the CMB, where you see it as a causal inference. You try to explain the data causally. They never use the word causal anywhere in any of their papers. Actually, nor do I, because I only realized this recently that this is causal. Blah, blah, blah. Oh, I love this one. This is K2 data. This is when the Kepler satellite was missing some reaction wheels. It went into this K2 mode. This is very relevant to TESS right now, though actually TESS is better than K2. But up the top, you see a light curve for a star. That's the measurement of the brightness of a star over time. You see how it's oscillating wildly. Actually, if you look at the y-axis, it is not oscillating wildly. It's oscillating by few thousand parts per million. So it's actually perfectly steady. But if you zoom in like that, you see this crazy pattern. And the green line going through those points up there is our instrument model. So you see the instrument model can be really, really complex. And the instrument model was trained on data that did not include this star. So that's a prediction for the behavior of that star. And you can see the residuals when we take that out. So the instrument model can be really complex, and it has to be really complex in hard experiments. By the way, this is also interpretable. I'm about to say that these models are uninterpretable, but this model is actually interpretable. Every one of those spikes is a thruster firing, and you can see in the first half of it, the thruster firings go one way, and in the second half, the thruster firings go the other way. You see that? That's because K2 went through from positive solar torque to negative solar torque at the center of the observation. And so the thruster firings were doing the opposite thing for the second half than they were for the first. So this is actually completely interpretable, which is sad for me because I'm about to say nothing can ever be interpreted. Good. A really important example is astrophysical foregrounds, and I was just going to flash some pictures. These are the Planck data, which is currently the best measurement of the cosmic microwave background, both in NYU asked. But on some scales, this is the best measurement of the cosmic microwave background. And you can see that there's this kind of isotropic snow, and then there's a line through the middle. That's our own galaxy, and that line gets bigger and bigger as you go to higher frequency observations. And that's because the galaxy that we're looking through has a different frequency structure than the cosmic microwave background, and that gives us a causal handle to separate them. And then that's been done very well with machine learning. Not actually separate that. Oh, this is my favorite. We're on the Earth, and the Earth is orbiting the sun, and the Earth orbits the sun at 30 kilometers a second. You know that? Anyway, that means if you're observing a star, sometimes you're moving towards the star at 30 kilometers a second, sometimes you're moving away from the star at 30 kilometers a second. As you do that, the atmosphere is going with you. You're with the atmosphere, not with the star. That means if you look at the atmosphere and the star, they shift with respect to each other over time spectrally because there's a Doppler shift, right? And so you can separate the atmosphere from the star completely data-driven. So on the right side where you see Barnard's star there, the black dots are the data we have, and the red and blue lines is a completely data-driven separation of the stellar spectrum from the atmospheric spectrum. The star is the red line, the atmosphere is the blue line. Completely data-driven, and it's more sensitive. This finds atmospheric lines that people didn't know about, like there aren't unidentified atmospheric lines appeared in this. And look at those data. If you look at those black data, and I asked you which of the lines in that black spectrum are caused by the atmosphere, you go But a data-driven model can easily separate. And by the way, the sum of the blue and the red lines is the black line. Said. Good. Here I'm back to causal inference. Just a side note: the social and medical sciences talk about causal inference all the time, but astronomers rarely do. And I think a lot of things we describe a lot of results in causal language in physics, which is kind of weird because we believe in unitary evolution from the initial conditions. When my daughter says, "Why are the dishes in the sink dirty?" I say, "Because of the initial conditions of the universe plus unitary evolution." Because that's why. I mean, if we do live in a deterministic universe, if we live in a Hamiltonian or Lagrangian universe, it really is that. But we say counterfactual things all the time. We always say, "Well, if we'd observed the star differently, we would have got this different thing." Strange, right? Anyway, there's an open question of how to describe causal inference and counterfactual claims in the context of a unitary evolution universe. If anybody wants a real theory. Oh, good. Now, when I die, by the time I die, I've taught the astronomical community exactly one thing. This is the one thing I want it to be. All data analyses are subjective. There's no such thing as an objective answer or an objective data analysis. You always must make choices when you make a data analysis, and those choices are made by you. They were not handed to you by God, and therefore they depend on your past experiences and what you think is important, and therefore they are subjective. And I often say this, and people are like, "Oh, we're finding objective truth." Well, you might be finding objective truth, but you're using subjective methods, undeniably subjective. And I don't know any way to separate out causal structure except by subjectively putting it in or asking for it at the beginning. Now, so now there are claims that you can learn causal structure directly from the data, and there are methods for that. But I don't believe they are interpretable. So it is true that you can run some method which tells you that there's a graph, that you can generate your data on a graph that's sparse, and you can interpret that as a causal claim about the data. But if you're using machine learning components, I do not believe you'll be able to determine what the nodes of that graph correspond to, or what the links in that graph correspond to physically. But maybe somebody will get interpretability and explainability working in this room, and then good. Yeah, then we'll just learn the causal structure, we're done. Then it'll probably also tell us what we're wrong about in the standard model of particle physics. And I actually think that interpretability is impossible, and my fundamental argument is the last line there. I think machine learning is powerful because of model capacity, and capacity comes at the expense of explainability. So here's my proposal. I'm making a proposal now. Generative AI for observational data and answering Sid's question. I believe you should put a beautiful, simple, interpretable, covariant physics model in for the things you care about. You should put in a horrifying, complex, uninterpretable, but still covariant machine learning model for the auxiliary effects, the physics that you don't care about, but you know is there. And then you should add a horrifying, complex, uninterpretable, and not even a covariant model for your instrument parameters, calibration, selection effects, and all those things. And then as long as you have diverse enough data, these things will be separately learned. They have to be diverse enough that you see different mixes of the fundamental model, the auxiliary model, and the instrument in different data points so that they can be separate. So that the thing can see that the situation is sparse. And then that leads to foundation models, because you might think that some of these things are foundation models. Maybe your horrible model of your instrument is a foundation model that can then explain any data taken from that instrument ever, or maybe any data in a whole family of instruments of that type. So this could be a way to structure a foundation model. So instead of thinking of the foundation model, we just throw all the data in and then throw a big model on it. We might want to throw the data in, but tagged with housekeeping data about where it came from, and have different parts of the foundation model attend to that housekeeping data. Something like that. Anyway, I'm being vague here because I don't actually know how you do this. I just wanted to say that we actually have found that the foundation model idea has been very useful. This is a little paper we wrote last year on the Gaia data release 3. We were able to show that we did a better job of getting scientific information out of the Gaia data if we forced the model to also predict the SDSS spectroscopy. So if we forced the model to also be able to successfully predict external data on those same stars, it did a better job of putting labels on all the stars, whether or not they had the external data. So like forcing the model to attend to not just the data we wanted, but also to attend to other tasks, like multimodal tasks. Like giving the model multimodal tasks, we got better predictions for the things we care. And I think that is it. Yes, thank you. Questions? Jesse.
Thanks for the talk, very fun. Just in terms of a nomenclature that may or may not be helpful for you. Sometimes when we talk about gauge symmetry, we use the language of gauge redundancy.
Yes.
Redundancy is helpful, at least in the part of this, maybe we get ourselves not confused about what they are.
Good. Yes, in fact, all of the passive symmetries are actually functionally redundancies. Like the fact that you can use different coordinate systems is a redundancy in the room. You can just relabel all the vectors. Yeah, good. I like that.
So there's many things that I could poke you on, but since we're here about generative AI, you said something or implied something, and it's hard to tell if we're joking or not.
That was deliberate.
In your brain, if you have a generative model, or you have a box that I can poke and get draws from a generative model, are those the same thing in your brain or different things in your brain?
They are very slightly different in my brain because I believe that, I believe that a model, like let's forget the machine learning nomenclature and just actually ask what the English word generative means. I believe a generative model is a model that could in principle give you a sample of a piece of data. Whereas I think in machine learning, it means something that easily produces samples of data. Like if I have a likelihood function, I build likelihood functions for a living, I do precision measurements, so obviously I build likelihood functions for a living. Most of the likelihood functions we build, it would be very painful to take a draw from the likelihood function. So in my view, that is technically generative, but in fact, you would not actually do that.
And when you say the word build in likelihood,
Yeah.
you really mean I have a functional form?
Yes, I mean that I have an executable piece of code that takes a data set and a set of parameters of the model I care about and returns a log probability density, a log of a probability density.
So then just kind of keep poking. So if you ask what is easy or hard to do, there may be certain cases where I can code up that function as a function. And there may be cases where I code up I push a button and I generate an example. And in your brain, those are different ones.
Well, yes, in the sense that in the sense that one of them can be used to create an unbiased estimator and one of them cannot.
Which one?
So,
maybe I need to myself.
okay, so here's a joke. Frequentists take derivatives and Bayesians integrate. And if you need, see, at least one person laughed. If you need an unbiased estimator, you get a likelihood function and you optimize it. That involves taking derivatives. If you are taking samples, why would you take samples? Samples are only ever taken in order to compute an integral. Actually, that's not true anymore because you freaking machine learning people. But the only reason I ever take a sample is to do an integral. So Bayesians are sampling things, they want to sample posteriors, not likelihood functions. So functionally, they're very different. In terms of what you can do with those two functions, it's very different. But the weird thing is, if you have the one where you can compute the log probability, you could always sample from it, at least in principle. Whereas if you have the one you can sample from, you can't necessarily compute that log probability. By the way, I just read a bunch of the literature on normalizing flows, and it's very beautiful on these subjects, because normalizing flows, you learn the functions in both directions. And which one is more computationally tractable sets which of those operations you can more easily do, which is very interesting. The normalizing flow concept is actually a very beautiful concept.
Speak a bit more about why you think coding at variance would break optimization. Because our experience was that enforcing at variance is better.
Good. I'm good.
And that's for small models, right? It's not big.
Yeah, good. I don't actually think it slows down optimization. That is not what we have found. In fact, when we added equivariance to these toy problems, we trained much faster. So I don't actually think it slows down optimization, but a lot of people in the kind of stochastic gradient world believe that it's helpful to you that your latent space has all this freedom and all these degeneracies. And I don't know when that is or isn't true. And some people I highly respect tell me that it's bad to put in the equivariance, so I'm struggling. So I'm not saying that I wasn't intending to say that it hurts optimization. I was actually intending to argue that it won't hurt optimization, but I don't have a general argument.
I'll say, as an organizer, I haven't answered to this, but there's gonna be a speaker, at 11 tomorrow, who actually completely disagrees with the statement, and you should ask him because he explained to me why, he's got the right answer. Like, why it's actually sometimes better to throw this.
I think I do have an intuition that it might be very context dependent
It's, I mean, it also.
and symmetry dependent. You know, like group dependent.
Yeah, question.
Towards the beginning, you're talking about detecting pandas in an image. And you talked about there being a variant symmetry there. So one technique that's done with CNNs is image augmentation. So like you can rotate while you're training. Because if you don't do that, then you could have a situation where you get upside down pandas that don't get detected.
Yeah. No, in fact, one of we're interested in whether these equivariances are there naturally in CNNs in the wild. Like if you find a CNN that works well in the wild, we want to now analyze it. But of course, in some cases, people have actually trained it with augmentations that include funny mirrors. So if all they've done is plopped it like this or whatever, then that's a very small group. But if they've modified it in with elements of a much larger group, then we might get the equivariance there, not because it happens in the wild, but because they forced it in. And so that is actually critical. My conjecture, the conjecture I'm making is that even if they haven't done that, it would be diffeomorphism. That's my conjecture.
Sorry, can I add to that as well? So introducing that kind of variance through augmentation, it's fine if you have a large model with lots of data, because essentially it will learn to generate it will learn to generate the model parameters that allow it to work with training data, but it doesn't enforce the variance test. So it doesn't generalize.
Yeah, actually, one of the things that's interesting about augmentation, which has not been explored very much, is if you understand the weights and biases of your network well, sometimes you can actually do a group average rather than augmenting by adding data examples. With each data example, you could do a group average of the gradient. So you get a gradient, and then you could do a group average of the gradient under the group, and then only move in the equivariant direction. Then it's like infinite augmentation, but finite augmentations, I agree with you. It's a detailed technical question whether or not you have enough data and the right model capacity to see it.
I have a question. So you have these three approaches to when you want to use, equivariance to not use it. And the experimental approach, I completely agree, is never symmetric. And then, kind of the physics approach, eventually symmetry is coming. The problem is all my colleagues have a problem separating the physics background that they don't care about, and three, the experimental data. How do I sociologically convince these people that they have to split this? Because it's driving me nuts, right?
Yeah, I don't have a very good, that's directly to this slide. I don't have a very good, we work on the radial velocities of stars. When you measure the radial velocity of stars, the instrument calibration is obviously there because we need to know exactly the Doppler shift. The star is definitely there because it's got a spectrum. It's got a rest frame spectrum, and we're trying to find the shift, Doppler shift, and rest frame spectrum. What's our auxiliary model? The auxiliary model is the fact that the star has a convecting, differentially rotating surface with spots and flares and stuff on it. And we traditionally have folded all that crap into the instrument as if the differentially rotating convecting surface of the star is part of our spectrograph, which it definitely is not. And actually just now we're working on a project to actually build a physical model of the surface of the star. Because if we build a physical model of the surface of the star, we can impose all the symmetries that exist on the surface of the star, like that it should decompose into a spherical harmonic spaces in a sensible way and things like that. And then forward model into the data. But notice that was a choice, it was a subjective choice, and it wasn't unreasonable to do the one and it isn't unreasonable to do the other, and one's much easier and one's much harder. And so I think there's always, I would like people to think about things in terms of these three levels, but you don't have to, in the sense that it really is subjective choice, how you split your model. But I have this intuition that you will succeed better if you do this, because you can put more structure on the problem if you do this. And I think, but I'm a believer that adding structure helps. Other people in machine learning believe equally strongly that structure hurts, you should let the data find the structure. So that just shows how out of touch I am.
The other question.
Yeah, so this idea of initial, but like automated theory regressions, opposite adding sense, wondering if that's talk about.
Yeah, so I haven't thought, yeah, I actually have thought a lot about automatic theorem proving, because I think that's so interesting. I don't know how many people know this, but there's a big chunk of the mathematics community that's trying to establish all of the bases of mathematics, the current basis of mathematics, with machine generated proofs. And I was actually at a one-day meeting about this, and the papers are just so insane. It's so great. It's like the coolest area. That I don't think of that as having anything at all to do with data analysis or anything, but you're right that is, I almost think of that as a different part of artificial intelligence. So that, that's why I opened by saying artificial intelligence. I'm just going to talk about machine learning. Because I think there's these other interesting things, like I mentioned integer programming, like logistics operations, integer programming type things, some very intelligent systems that are operating now. And these theorem proving things, I would also put in a separate box personally. But there might be a relationship, because you could imagine if you could write down the deep beliefs of physicists, you could imagine that that top level model, the fundamental physics model, I don't know where I wrote that, where that you could imagine that fundamental physics model maybe is something that knows something about the structure of mathematics and physics, like deeply. Yeah, exactly. Yeah. So yeah, I always think of that first thing as something that humans would write. Element one is something that humans would build. But of course, a lot of people in this room are thinking about maybe that's something that could be built with generative AI. Maybe GitHub Copilot could write that.
Any other questions? All right, let's thank David again.